Hello, everyone. Welcome to the Full Spectrum series. My name is Nick Valentino. I am an assistant director in the Hajim School of Engineering and Applied Sciences, and I will be your host for the series. This is the third year of the Full Spectrum series, where we invite faculty to discuss and explain their fields in an effort to inform and educate prospective and current students, parents, and alums on the problems that engineers and computer scientists are trying to solve. So if you're watching this and you are interested in learning more about problem solving and about engineering, you're in the right place. So today, our first guest today is Dr. Paul Funkenbusch. Dr. Funkenbusch earned his PhD from Michigan Technological University. He's a professor of mechanical engineering and a professor of material science. He's also the Associate Dean of Education and New Initiatives at the Hajim Dean's Office. So Dean Funkenbusch, thank you for being here. You really have two full-time jobs, so we're grateful that you can help us learn more about mechanical engineering.
Thank you, Nick. Let me share my screen.
Yeah, great.
And I've got a big task here, so I'm going to get right to it. Let's see. There we go. Hopefully that's visible. Yep. So I'm here to introduce mechanical engineering, and I have two items on the agenda. One is I'd like to introduce to folks what is mechanical engineering, and the short answer is it's not, well, a partial answer is not just about automobiles. Most people think mechanical engineers, cars, right, or planes maybe, and it is that, but it's more than that. So the second thing I'd like to do is tell you a little bit about what mechanical engineering looks like at the U of R. So what is mechanical engineering? Well, if you just do a search online, you can come up with all kinds of different definitions: study of machines, mechanical systems, bodies and motions, lots and lots of different definitions. But mechanical engineering is extremely broad and extremely versatile. Not everything you see is mechanical engineering, but almost anything you see includes mechanical engineering. So from a car to a paperclip, spacecraft, there's an important element of mechanical engineering in almost any kind of an engineering project. Rather than try to give you a fixed definition, what I want to do is give some examples or an example of mechanical engineering and kind of give you some feel for the broadness and the versatility. And for my example, I picked something which has been in the news lately. That's the Webb telescope. On the left-hand side, you see some examples of those pretty images that everyone has been looking at from the Webb telescope. And on the right, you see an artist's rendering of what the telescope actually looks like. And the telescope is, it's wonderful optical engineering project. So our colleagues over in optics have done great work in that field. What they fundamentally need to make their telescope work is the following. They need a very precise shape. They need it to be in space. And they need the shape to be adjustable. So the mirrors have to be able to turn a little bit so they can change the focus or change where they're looking at it in the sky. So that's, well, overly broad, and I'll say that's the optics part of things, right? So how do we actually make this work, though? And when you talk about actually making something like this work, you get into the area of mechanical engineering. So let me just say, first of all, if the space telescope is operating in space, there is a very different environment than there is on Earth. So on Earth, we have gravity and we have reasonably comfortable temperatures. Space, there's no gravity, and there is a odd temperature profile, right? So it's basically very cold, but when the sun shines on it, there's also a thermal gradient potentially. And in order to make the telescope light enough to shoot into space, it has to be very thin. So you can imagine if you have a very thin structure like a piece of paper, gravity causes that structure to bend. So you have to be able to figure out, in order to get the right shape in space at space temperatures, what does the shape have to be on Earth at ambient temperature on Earth? So mechanical engineers are heavily involved in figuring out what that shape change is going to be based on the forces from gravity and the effects of temperature. What shape do I need to make on Earth in order to get the correct shape up in space? And that's really a mechanical engineering problem. Secondly, you have to take the telescope from Earth and you have to shoot it into space. So that's the realm of dynamics, the study of bodies in motion, orbital mechanics, how is it going to interact with the planets and the sun, and also things like power generation. So the rocket motor involves motion of fluid. So maybe it has, for example, liquid oxygen, liquid hydrogen flowing through it to produce the propulsion. How does that fluid flow inside the rocket? Those are all mechanical engineering kind of problems. Once it's up in space, it's packed up very tightly in order to fit inside the rocket. So now it's got to be able to unfold and deploy to the final shape. And after it's in the final shape, again, it has to be adjustable. So the parts have to be able to move slightly, very precisely to produce the new shape to get the image you want where you want it. And again, that's deployment, that unfolding operation, and the actuation, the motion of the parts of the telescope. Those are all mechanical engineering problems. The motors and all those sorts of things are really a mechanical engineering consideration. And finally, once you've figured out what the shape has to be and how small it has to be to fit inside the rocket, and all the motors that got to go into it to cause to actuate, you actually have to be able to design, manufacture, and assemble that. And again, those are all fundamentally mechanical engineering problems. So again, something which you think of as being sort of an optics or an astronomy kind of an item, there's an awful lot of mechanical engineering that goes into making something like that possible. Okay, so that's my example of mechanical engineering. Let's look at the U of R program. The U of R program really has two fundamental stems. We have a solid and material stems, which, as you can think of, is based on solid and materials, right? So on the left-hand side here, you see a little robot that's designed to roll over terrain. So a solid object with motors and it kind of designed to roll. That would be part of a solids or materials STEM of mechanical engineering. And then on the right-hand side, you can see a fluids and energy STEM. This is a human-powered vehicle. And again, there's a lot of mechanics there in terms of the wheels and all of that. But to get a human-powered vehicle, a really important consideration is making the wind resistance low, so it has a good aerodynamic shape. And that's all to do with fluids and energy, right? Flow of air past the human-powered vehicle. And then in addition to sort of those two main stems of solids and fluids, you have to learn teamwork, you have to learn systems, so you can put things together, components together to make a more complex system. You have to learn about designing everything, and you have to learn about communicating things. At the U of R, we try to do that. We do that, I think, successfully with a program that looks something like this. This is basically your course schedule for the 8 semesters that a student would normally be at the U of R. I've deleted all the math courses, the science courses, the writing courses, the English courses, anything except mechanical engineering has been taken off here. So I just want to focus only on the mechanical engineering. And again, you see our two stems there at the top. There's a solid material stem, and solid material stem starts with ME 120. ME 120 is statics. So ME 120 is the study of things which don't move. It's Newton's laws with F equals 0, okay? Following 120, you move into ME 121, which is dynamics. Dynamics is the study of bodies that move. So things like orbital mechanics, gravity effects, those are all going to come into play, and you're going to start to understand how those work in ME 121. Now, ME 121 kind of crosses the boundary between solids and fluids because you also look a little bit at the motion of fluids there, but mainly from the perspective of how does the motion of a fluid affect a solid body. Following 121, 120 and 121 have to do with objects which do not deform. So we begin to look at objects which do deform, which bend, like, for example, this telescope in gravity or absence of gravity. We begin to look at that in ME 226, which is mechanics of materials. So you learn how bodies deform. And then finally, in that solid STEM, you take ME 280, where you learn about materials, how materials are put together, what are the properties of materials, those sorts of things come in ME 280. On the fluids and energy STEM, we have ME 123, which is thermodynamics, ME 225, which is the motion of fluids, fundamentally, ME 223, which is primarily the motion of heat and energy. ME 213 is a sort of a systems course, which has elements of both solids and fluids. And finally, ME 251 is heat and power. So it's how do you make an engine? How does an engine work? What are the thermodynamics of an engine? So again, think about a rocket engine, how does that all work and fit together? So those are the two main stems. In addition, you need some computational skills. So you can see there's some courses in there which are computational. In some of the classes, there are labs mixed in, but we also have 2 courses which are dedicated entirely to lab work, and that is ME240 and ME241. And finally, at the end, as your capstone, your final project course, there's ME204 and 205. So you learn about how do you design things, working in teams, all those sorts of things are brought together. Everything is really brought together in ME204 and 205. So that's the broad outline of what you would take as a mechanical engineer. You start out fairly slow, and you gradually build along each of these stems, and then you combine all that stuff to put together a final project in the capstone design course. All right. One of the things that's nice about the U of R is the research and the opportunity for undergraduate students to get involved in research. I want to show 4 examples of research here. In the upper left-hand corner, you'll see a representation of 2 diamond anvil cells pushing together on a piece of material. This is an example of research from Professor Diaz's lab, and he looks sort of at the fundamental ability to create new phases, new structures of materials under very, very high pressures. In the upper right-hand side, you see a couple interesting structures. Those are actually structures with different types of materials mixed together. That's work that's done by Professor Abdul Rahim, and she looks at how those different configurations of materials stuck together at a microscopic level, how that affects the properties of the material. She was walking by about 15 minutes ago, happened to talk to her about this, and she actually currently has 3 undergraduate students working on this project. So she has 2 seniors and a sophomore working on this project with her at the current moment. In the lower left-hand corner, that's actually a brain. This is an example of work from Professor Kelly's lab. So one of Professor Kelly's projects is to look at the motion of fluids inside the human brain. The idea being that the motion of fluid is necessary to sort of flush out the brain and remove the waste products produced by the functioning of the brain. And efficient removal of those products may be important in avoiding Alzheimer's disease. So he's a fluid mechanics kind of a person. He looks fundamentally at the fluid mechanics inside the human brain. And then the lower right-hand corner is work that's underway in Professor Louis' lab, and he's looking at ocean currents. So the motion of fluids in the ocean, where energy is dissipated inside the motion of fluids in the ocean, important for things like climate change considerations and analysis of the atmosphere and the oceans. So again, mechanical engineering is incredibly broad. So we've got examples here at the top of solids and fluids. We've got examples of natural materials and artificial materials. Professor Diaz is looking at things at an atomic scale, and Professor Louis is looking at things at a planetary scale. It's all mechanical engineering. It's all research that's currently underway in the mechanical engineering department at the University of Rochester. So to close, I'll say, we also do automobiles. There's a Baja race team that works. I'm happy to answer any questions, but just put this up here. If people do want to contact us, I put the mechanical engineering department address on there. So anyone still write mail, I'm not sure, but that's where you can get in touch with us. If you're on campus, you can stop by the Hopeman building, obviously, and check in. I also put my email down there too, if there are questions that I can address. All right, thank you.
Yeah, thank you for that. I mean, even having experience with this as an advisor, the way that you broke it down, I think it's probably the best idea to start with stuff that doesn't move, right? You're saying
Yep.
that a lot of the stuff that does. So many of our full spectrum viewers are prospective students and parents of prospective students. So we'd like to know a little bit more about like how you got here and your outlook on mechanical engineering. So we want to go back to, just a few years ago when you were a senior in high school. I want you to talk about like, did you see yourself becoming an engineer? Did you see yourself becoming a professor? Like, what would surprise 18-year-old you the most?
Well, it's a really tough question. I think a lot of people have very interesting origin stories, if you will. Mine is pretty boring. I had an older brother who was a metallurgical engineer. And so I went into metallurgical engineering. My degrees are all in metallurgical engineering. But metallurgical engineering is closely allied with mechanical engineering. And so when I was looking for a job, University of Rochester had an opening in mechanical engineering. And so I ended up here. I never really thought about whether I'd be a professor or not. I knew I wanted to do research. And so I was sort of directed towards either university or maybe a company lab. or even a government lab, but the university stuff just kind of developed in terms of where I ended up.
So as your experience with an undergraduate, can you talk about some of the opportunities you had outside of the classroom as compared to how the opportunities students might have when they come to UR?
That's a good question. So my opportunities for doing things kind of on campus were much more limited. We didn't have a Baja team, for example. We didn't have a lot of the club activities that are very common here. So I didn't have that kind of an opportunity. There was research underway in the department, and I did some small projects in research. But I gotta say, this is 30 years ago. The opportunities in terms of the kinds of research and the scope of research, just there's no comparison between what I had and what's available here at the U of R. It's just immeasurably more.
So you talked about this in your presentation. I just wonder if you can go into more detail about the misconceptions about mechanical engineering, where we think of structures, right, as being, a lot of times students will cite structures like I've read a lot of common application essays that talk about, I got interested in Legos and that led me to other structures, and that's why I'm interested in mechanical. So can you talk about the biggest misconceptions in mechanical engineering, and what can we do to counter that?
I think it's really that the mechanical engineering is sort of hidden in almost everything. People think of, again, they think of the Webb telescope. They think of that as being optics. It's or astronomy. They don't realize the engineering efforts to get it there, and they don't realize that most of that engineering effort, or a large part of the engineering effort, is mechanical engineering. There's some objects which are obviously mechanical, right? So you think cars, you think robots, but almost everything has mechanical engineering elements, and people just don't appreciate that's an important part of things.
So looking forward, what do you think the next big thing or wave in your field that current and prospective students should pay attention to?
Okay, I would say from a tool standpoint, it's probably computation. It's becoming more and more possible to simulate things and to look at things using very complicated computer models. Computing power is becoming much more readily available. Techniques are improving a lot. So from a tool standpoint, I think the ability to do computational kinds of things and to process large amounts of data, so things like sort of data science or quasi-data science, I think that's really important. From an application standpoint, there's just incredible opportunities all over the place. One of the most exciting things for me personally is all the SpaceX and the private space ventures that are going on. We developed the whole rocket technology and space exploration as a government project, and it was great. And we did some basic exploration, but in order to really kind of get out there and make space a part of everyday life, take full advantage of it, I think the private opportunities that are coming through with all those rockets are really exciting. On the automotive front, electric cars, even the cars which are not electric now, the drivetrains and the power systems are all changing to be electrically driven. Even if the engine is internal combustion, the drivetrain itself may be electric. Self-driving cars, that's also a really big opportunity. And then just in the energy area, right? So the obvious one is windmills, right? Those huge blades whipping around. That's obviously a very big mechanical engineering problem. But even anything like solar cells, geothermal, all those kind of problems involve mechanical engineering technologies and mechanical engineers working on them. So I would say the energy is kind of an additional really big application that's coming on board.
Great. I mean, at heart, I'm always an advisor, so I like hearing other people's advice. So what type of advice would you give to people who are interested in starting to learn more about engineering or starting their journey in pursuing mechanical engineering?
So if you're talking about somebody in high school, the best skill I can say you can get is, or you can nurture in yourself, is to kind of ask why things are built the way they are. That basic inquiry, not just sort of, why is something the way it is, but why did someone think to make something the way it is? If you can nurture that skill in yourself just by looking at common objects and kind of trying to figure out, well, why is the handle here, and why is this designed that way? I put together a desk a few years ago, and big assembly project. I put one of the desk drawers in backwards and it locked in place, and it was essentially impossible to remove, right? So I sort of cursing at the designer of the desk. A little bit of thought on that design. If the person had designed it so it only fit in one way, that would have made things much better. And as I look at other things, I look at the design, I think, hey, that was pretty clever. They thought to make it so that it only fit together the right way, so that it's sort of idiot proof. I couldn't do it wrong. So quizzing the items you see in your everyday life and trying to figure out why they're put together that way would be one way I would say to start to think like an engineer.
Well, you've given me a scapegoat for every time that I try to put something together and it doesn't work. It was a design flaw. I don't.
It's bad design. No, that's my go-to too. If I put something together and it's wrong, it was badly designed. Yep.
Dean Funkenbusch, thank you for your insight and for spending this time with us. We really appreciate, especially the ability to talk a little bit about your field and get people excited about it. So thank you very much.
Thank you, Nick. Thanks for the opportunity.
The Full Spectrum series will return with other areas such as biomedical, chemical, audio and music engineering, and much more. So please feel free to share this video. We'd like to expose this to as many people as possible so that we can use this as a resource in trying to figure out what's next for you. We started the Full Spectrum series online during the pandemic, and we ended each video with "We hope to see you soon," because we really did. So even though we're back in person, I think it still applies. So on behalf of the Hajim School, thank you for watching, and we hope to see you soon.